This is the next lecture of the geometric modeling course. We start with the Constructive Solid Geometry, abbreviated as CSG. It is based on several three-dimensional solid primitives and regularized set-theoretic operations. In this lecture, we will recall the basis of the set theory. Then we'll discuss special regularized set operations. The next is to introduce the data structure called a CSG Tree and the associated procedure called the point membership classification. We need to mention special cases of CSG objects and null objects. The classical implementation of CSG, the PADL2 system, will be characterized. The term set denotes any well-defined collection of objects. It can be a flock, a pack, and many other different things. The universal set E is a set that contains all the elements of all the sets under consideration. A null set is a set which has no elements at all. Set A is a subset of B if every element in A is contained in B. There are many operations on sets called usually set operations, set-theoretic operations, or even Boolean operations. We need to recall the main of them, such as union, see the symbol on the slide, intersection, complement, which contains all elements in E that are not element in A, and difference. The geometric interpretations of set theory notions are the following. Sets, or geometric objects, consist of points, and the universal set E is the set of points defining the entire space. The shown expression P belongs A means that the point P is included in or belongs to the set A. On this slide, you can see Venn diagrams of discussed Boolean operations. It is a convenient way to represent set-theoretic operations when the number of considering sets is less than 4. An example of the Venn diagram for 3 sets is shown in figure D. Venn diagrams for higher number of sets exist, but they are not so easy to work with. A boundary point of a set A has in any its neighborhood both points that belong to A and that do not belong to A. The boundary BA is the set of all boundary points of A. The interior IA is the set of all points that belong to A, but not boundary points. An open set does not contain its boundary points. Closure KA of an open set is the union of the set with all its boundary points. To introduce CSG properly, we need first to define regularized sets and regularized set operations. Let us look at the object defined in the figure A by its interior points and boundary points. The object has dangling and unattached points and lines. Not all boundary points are included. It is called a non-regular solid. Figure B shows closure of the object. All boundary points are now a part of the object. Look at figure C. We take now only the interior of the object. Dangling and unattached points have been eliminated. Regularization of the object is the closure of its interior. This operation is illustrated in figure D. A regular set equals the closure of its interior. In practice, it means that all dangling and disconnected lower dimensional components are eliminated and the boundary is completely included in the object. Regularized set operations mean that first, standard set operations are applied and the regularization is applied to the result. This image shows the difference between standard and regularized operations. In the case of the standard operation, the result of intersection is empty only in the last case, where the objects do not have common points. In the case of the regularized intersection, only the first operation will have non-empty result. In all other cases, the lower dimensional results are removed by the regularization. One more illustration of the regularized intersection. For two solids placed as shown at the top, the standard intersection produces a block with dangling segments as shown at the bottom left. But the regularized intersection produces only a block shown at the bottom right, and the dangling segment is removed. Note that the asterisk is used to mark a regularized operation symbol. This example is a 3D version of the previous one. The dangling wall is removed by the regularization. In constructive solid geometry, simple primitives are combined by means of regularized set operations and rigid motions. Standard CSG primitives are block, cylinder, sphere, cone, and torus. These are other and more rare CSG primitives: prism, upper left; tetrahedron, lower right; fillet, upper right; wedges, lower left and upper right. A CSG object is represented in a modeling system by a special data structure called a CSG tree, including primitives, linear operations, translational rotation, and regularized set operations. Primitives are placed in the leaves of the tree, and operations in the nodes. For example, for the presented object, the CSG tree at the right includes three primitives in the leaves: two boxes and a cylinders, three translation operations, and two regularized set operations: union and difference. These are more complex CSG trees with the primitives and intermediate solids drawn in the nodes of the tree. Just 8 primitives make a quite complex model at the left. Modeling operations create the CSG tree, while the main analysis operation is the point membership classification, or PMC. Let a solid S and a point X be given. A typical query is to analyze: is X inside, outside, or on the boundary of S? The PMC function can be defined as shown at the bottom. It has three possible outputs indicating that the point is inside, outside, or on the boundary. The PMC procedure uses the CSG tree for the evaluation. It is based on the divide and conquer paradigm. First, the point membership is detected for the primitives as A and B on the slide. Then, the regularized operator OP is applied to the results, and the PMC for the entire solid is evaluated. This is a pseudocode for the PMC procedure. Prim-M is a primitive classification procedure and must produce in, on, or out answers for a given point. Combined procedure applies set operations with tree-valued logic to its arguments. First, the left subtree is processed. Then, the right one and the results are combined. The PMC algorithm has a recursive structure. Coordinates of the given point are sent to the root of the CSG tree. Then the coordinates are recursively propagated into the tree down to the leaves, possibly altered by the linear transformation nodes. At each leaf, the final point coordinates describe the same point, but in the local coordinate frame of the primitive solid. This point is classified against the primitive. There are several cases for the downward propagation procedure. If the point xyz arrives at a set-theoretic operation node, it is passed unchanged to the two subtrees. If the point arrives at a motion node with a linear transformation, the inverse transformation is applied to coordinates x, y, z, resulting in new local coordinates x prime, y prime, z prime, which ascend to the two subtrees. If the point arrives at a leaf, the point is classified against the primitive, and the classification is returned to the parent of the leaf. The downward propagation is followed by the upward propagation. Classifications from the subtrees are combined in the set-theoretic operation nodes. No work is done at the linear transformation nodes. These tables show the combination of point classifications for union and intersection operations. Classifications for one primitive or subtree are shown in the left column and for another one in the top row. The elements of the table show the result of the operation. There is an ambiguity for the on-on classification which requires special treatment. Let us consider an example of the on-on ambiguity for the regularized intersection. In the left situation, where one primitive is inside another and they touch by the boundaries, the on-on situation has to result in the on, because the point belongs to the boundary of the intersection solid. In the right situation, the result has to be out, because the intersection solid is empty. The on-on ambiguity shows that the classification of a point in a regularized set operation node cannot be computed only from the subtree classifications. The additional information for resolving this problem is given by a neighborhood of the point. Accurate regularized operation algorithms use point neighborhoods. To resolve the on-on ambiguity, we need to know which points near the point P are elements of solid S. There is a formal definition of a neighborhood. A neighborhood of radius r greater than 0 of a point P with respect to S is the intersection with S of an open ball with radius r centered at P. Here you can see how to perform point membership classification using the neighborhood. P is inside of S if and only if it has a full neighborhood. In other words, then a neighborhood equals the closure of the ball. P is outside of S if it has an empty neighborhood. And P belongs to the solid boundary if every neighborhood is neither full nor empty. Two types of boundary points with their neighborhoods are shown in the picture. There are face and edge boundary points. Now you know enough about neighborhoods for resolving the on-on ambiguity. Let us consider regularized intersection operation for two examples in the slide. In the case A, the neighborhood classification allows us to classify the point as a boundary point in both solids. The intersection of two neighborhoods also provides the condition of a boundary point. The same procedure for the case B gives us an empty set. This means that the point is out of solid. We already know how to classify a point against a CSG solid. Now let us see the algorithm structure for the curve solid classification. This is important, for example, for the effective rendering of CSG solids using ray tracing. The first step is the downward propagation. The line curve description is sent to the leaves of the CSG tree. In a leaf, find the intersection points between the curve and the surface of the primitive. Partition the curve into segments labeled in, out, or on the surface of the primitive. The second step of the curve solid classification is the upward propagation. We propagate the segments upward from the leaves to the set operation nodes. Then we merge the labeled segments in accordance with the operation. This example shows two primitives of the CSG solid and a straight line being classified against the solid. The classification against the left primitive results in two in-segments of the line. See the line marked by L. The classification against the right primitive results in one in-segment of the line. The lower lines illustrate the union, intersection, and difference operations applied to the line segments obtained from the classifications. The lower images show the corresponding solids obtained from two primitives with union, intersection, and difference. There are several special cases of operations between primitives in CSG trees. The left image shows the union of two disjoint primitives. Both primitives are included in the result. The right image shows the difference of two disjoint primitives a and b. The primitive a remains in the result unchanged. The left image shows the union of two primitives, where the primitive a wholly contains the primitive b. The result of union is the primitive a. The central image shows the difference of two primitives, where a wholly contains b. This is a normal situation, and the whole is created in a. The right image shows the difference of the inverse of a and b. The result is the empty set. In the case of difference operation in the left image, the result has two disjoint solids, parts of the primitive a. In the middle image, the regularized union of two tangent primitives makes one solid and the joint boundary disappears. The union of the right image creates a solid with the inner loop or cavity. In some cases, a complex CSG tree can represent a null set. This can be the result of not careful modeling. The shown complex solids, A and B, are modeled such that pins in B fit two holes in A. The intersection of A and B produces the null object, and complex modeling has no sense. However, this intersection can be applied in order to detect if two solids have inappropriate intersection. In this case, the null object is a good result. A redundant subtree is one that can be eliminated without altering the object defined by the CSG tree. If a tree represents empty space, it is said to define the null object. The problem is for two given solids, A and B, determine whether or not their intersection is empty. Applications for such a collision detection, packing studies, and design verification. Let us suppose that in the process of modeling, first an L-shape was created by union of two blocks and a vertical hole in one of them. Later, a plug is added to the model, and union is made with it. The resulting object has no hole, but the CSG tree has both, the hole and the plug. It can be simplified as shown at the right by removing the hole and the plug subtrees from the tree. Another case of a CSG tree reduction. Two objects touch each other at a single point. The intersection operation in the root results in an empty set. It is better to simplify this object to a null tree. It is the time to give an example of a practical modeling system. PADL2 is a hybrid CSG BREP modeling system with CSG as a primary representation. The core system can cover from 19 to 95% of typical unsculptured industrial parts. The domain is the class of objects representable by compositions of planar, cylindrical, conical, spherical, and toroidal half-spaces. Using the regularized set operations, union, intersection, and difference, plus an aggregation operator for assemble and rigid motions, translations, and rotations. System characteristics are the following. Informational completeness. The core system should contain at least one formally complete, unambiguous representation scheme. It is CSG in PADL2. Validity and consistency. Nonsense objects should be excluded automatically. Extensibility. The design should permit geometric coverage to be extended and new applications to be supported without redesign of software. Efficient support of diverse applications. Alternative representation schemes should be supported. It is the boundary representation in PADL2. Environment. The system is almost 30 years old. It was implemented on 32-bit medium-sized virtual memory computers. The PLDL2 development system was a VAX 11/780 running the VMS operating system. Software is implemented in Fortran 77 for portability. Three main input interfaces are: first, interactive curve editor plus curve to CSG converter. Second, general set of callable routines in Fortran 77. The third, invertible text representation. CSG graphs can be inverse translated into text. Solid definitions arising from any input modality can be archived, edited, and used by other definitions. This example gives an impression of the procedural solid definition in PADL2. The prism is described as an intersection of three blocks. This is a nail modeled using one intersection and two union operations. See the nail root description line. CVLease is a modern set-theoretic solid modeler implemented as a library of C++ classes. Its feature is extensibility of primitives. Any primitive can be added with its defining function evaluation procedure. Algebraic operations are allowed on the level of primitives. Then, a pure CSG tree is constructed on thus defined new primitives. It is an open-source software under the GPL license. The book by Foley covers CSG as well as other solid models. More special references are given on the next slides. Here is the list of additional geometric modeling references used to prepare this lecture.